is on computing summaries of string loops in C for better testing and refactoring. And the talk will be given by Timotei Kapos.
Okay, hello everyone, I'm Timotei, and today I'm going to talk to you about some work we did with our collaborators on computing summaries of string loops in C. So as a quick taster, consider this simple loop in C. It iterates the string line from the start up to the first non-white space character. Now, if you're familiar with your libc, you might recognize that this function is similar to stir-span, and in fact, it can be rewritten as adding the result of stir-span colon line and the white space characters to line. And in this talk, I'm going to show you an automatic technique of how we do this summarization on this loop and similar loops. And the reason we would want, like the main reason we would want to do this is to give clarity to the meaning of loops, because it's easier to reason about something you know than an arbitrary loop. And we believe this has uses in refactoring program analysis, where we mostly focus on symbolic execution, but it's more general, and potentially compiler optimizations. So if we look a bit further into these motivations, for refactoring, consider a different loop, which is a bit more complicated, which iterates the string path from the back up to the first forward slash. Now, this is basically a stir-rchar function, which looks for forward slash, but it has a slightly different handling of the case where forward slash is not found. So our technique calls stir-rchar and then add some conditional on what happens when there's no forward char in this ternary operation. And so these two examples I've shown you are real examples from wget and bash, and there are many others. And we found that C code that we looked at contains lots of loop that replicates these libc functions. There are a couple of reasons for this, and one of them is like different handling of edge cases. Other ones are just developers being more familiar with loops than libc functions. So for program analysis, I believe that it's easier to reason about a known function that you can model somehow than an arbitrary loop. So as an example, consider symbolic execution of stir-char. There's the loop view of the world, where you just treat stir-char as a loop. And the way you would model this in symbolic execution is you would unroll the loop and gather the constraints of the loop condition and then pass it to the solver. The other one is you can just look at stir-char and realize that it's basically a first index of symbolic strings, and you can just model it in theory of strings, which can be potentially faster. Now, before you all get too excited about this, I want to talk about the scope of these loops, because we severely limited the scope of the loops to only talk about loops that operate on basically this interface, which they're loops that take in a single pointer and output an offset into it. But the most important restriction is that they only read the character under the current pointer, so they traverse it once and read that. And first, we needed a vocabulary to express these sort of loops that fit the scope. So if you remember the example I started this talk with, the way we would express it is as two instructions, basically. One is a stir-span instruction, which has some sort of payload, which is the second argument of stir-span, and some data terminator, so you know where it ends, and the return one, which basically says this is the end of the summary. And this is what represents our loop summary. And to simplify things, we just assign some pretty much random characters to this strings. So this sequence of 5 characters is what we would consider a loop summary. And this sequence of characters, or this vocabulary, has meaning with respect to this interpreter. So if you give this sequence of characters as a program to this interpreter, it should have the same behavior as the original loop. This interpreter is like fairly simple. It has the pointer-to-pointer interface we described. It has this result register, which gets set to input, and then it iterates the program for each instruction, branches it, and performs the action. So it either returns, or the stir-span instruction calls stir-span with the data from the instruction. And adding new vocabulary is as easy as adding a new case here. So to give you a big a brief overview of the vocabulary we used here. It's mostly string gauge functions such as stir span and stir char, some simple pointer manipulation, some conditionals, and some special characters that enable like traversing backwards because the default is forwards. And then the problem of loop summarization is finding sequences of these characters that when executed by the interpreter have the same behavior as the original loop. And the way we achieve this is with a counterexample guided synthesis. And the counterexample guided synthesis works by having you have a synthesizer and a verifier. You give a loop to the synthesizer. You generate a sequence of characters fitting all counterexamples. So you have some counterexamples you encounter so far, and you start with no counterexamples. The verifier says if this is true, and if it is, you're done. Otherwise, you fail and generate a counterexample, and the process repeats. To briefly talk about what we used for this synthesizer and verifier, they're both symbolic execution. And for a synthesizer, we use a symbolic string, which is essentially a symbolic program, and constrain it to be equivalent on all the current concrete counterexamples. And then we ask an SMT solver for a solution. On the verifier side, we have a concrete program, but we have symbolic inputs, and they're bounded to be of length 3. So we basically do a bounded checking up to length 3 of our program. And what's important here is that we prove in the paper that for loops in our scope, checking for length up to 3 is sufficient to show equivalence for arbitrary length. This basically works because each loop iteration doesn't really know where it is, so the second iteration is indistinguishable from any further iterations. And what I think is cool about our implementation is that both of these are a single run of symbolic execution. Now, I want to walk you through our stir span example of how this synthesis works. So we have our loop. We give it to the synthesizer, which has some set of counterexamples initially empty. And then the synthesizer comes up with a program that fits all counterexamples. At this point, there are none, so it's basically random. And here I choose that it just generated program F, which is equivalent to just returning results. Basically, it's an identity function. The verifier then goes along and tries to prove that this is equivalent to this up to length 3. Founds a counterexample, which is just space, which is a true counterexample, because our program just returns the 0th character, and the loop would skip over this space. So the synthesizer adds this counterexample to its cache and generates a new program that fits this counterexample. In this case, it's a stir span of space, and then we end. And the verifier finds another counterexample, which is just the tab character. Finally, the synthesizer comes up with an example that fits all the counterexample. The verifier is happy, we're done, and we found our summary. Now, we evaluated this by gathering loops from 13 open source programs in here using a semi-automatic process. And we extracted 115 loops fitting our scope. And in total, our technique was able to synthesize 88 out of 115 loops. As a first experiment, we ran 2 hours per loop. So we gave 2-hour timeout to the counterexample guided synthesis, and that managed to synthesize 77 out of 115 loops. That will tell you how we got to 88 in a second. And this graph shows the mean and the median time to synthesize loops over the programs we had. And the 2 things to note here, that mostly it doesn't take the full 2 hours. It takes about 5 minutes on average, such as here. But the interesting thing is that, like, for some loops, such as for some programs such as libossip, mean and the median are very different. And that's because most loops kind of are synthesized quickly, but for libossip, like 1 or 2 take over an hour, and that's because they are a bit longer, as in they have more white space characters, so the programs they have to generate are longer. So next, we wanted to measure the impact of timeout of counterexample guided synthesis, and program size on the number of programs we can synthesize. This graph is a bit dense, but that's the best presentation I could do. So the number of synthesized programs is on the y-axis, so how well it performs. And then on the x-axis, we have the maximum program size, so the maximum number of characters we can have in our summaries. And each individual column represents a timeout we gave. So we have a 30-second timeout, a 3-minute timeout, 10-minute, and 1-hour timeout. You can see that for like for program size of 1, we can't do anything because that's not enough to express any programs. But with program size 4, we can already do like 20 of them. And you will notice that all timeouts are kind of similar, which means that those loops are so simple that you don't need much time to synthesize. But with program size 5, with 30-second timeout, we are still at about 20 loops. But with just 3 minutes, we are already synthesizing a vast majority of the loops. And 1-hour timeout just gives a bit more. And then going to program size 6 gives you slightly more loops, and then it kind of plateaus. So then we looked into trying to optimize the vocabulary. That is, find a subset of vocabulary that synthesizes more loops than the full vocabulary. And we use Gaussian process optimization with a 5-minute timeout for loops. So before we had 2 hours. In this experiment, we have 5 minutes. And the best vocabulary, which is shown on here, was able to synthesize 81 loops with 5-minute timeout. We can combine that with the loops synthesized with the 2-hour one, you get to the 88 number. So for example, this vocabulary doesn't have stir char, and there were some stir char loops. This shows there is some bias in our data set toward stir span in particular. Next, we look into the impact of these loop summaries on symbolic execution. And the idea is to use them to gather more efficient constraints. The way we did this is intercept calls to stir functions and encode them in theory of strings and compare them with the vanilla CLI approach of where we compare with character by character constraints. And the idea here is that theory of strings should have an advantage for longer strings. We implemented this in CLI. And what's important to note is that we compared only on the loops we extracted, so not on the full programs they come from. This graph shows, so on the y-axis you have symbolic string length, so the length of the inputs that you have. So the length of symbolic inputs that the loops operate on. And on the y-axis is the mean time to execute the loops. So you can see that the constraint base, or vanilla CLI, kind of increases quite a lot in steps, which just indicate this was done with like 4-minute timeout. So different classes of loops start to time out. And when we gather with theory of strings approach, it's kind of just flat, and you can't even see it increasing. And if you zoom into the speedups for length 13, which was somewhere here in the middle, you can see that most loops have like significant speedups of like over 100x. There's one loop that has negative speedup, but this is just an outlier because it's a loop that terminates in under 1 second. Next, we looked at the compiler optimization potential, where we compare the loop summaries, so the libc library functions, with heavily optimized compiled loops. And here, not that surprisingly, the loop summaries are slower in most cases, but there are some cases where it's faster. And so the cases where it's faster are like stir char loops, where you can use vectorization. And the slow cases are mostly stir span loops, because the libc implementation basically builds a table at each call, which is expensive if you just have like a couple of characters, which is what all the loops we have. finally, we used some of the summaries to create patches and send them to developers. And developers of libosib, patch, and wget actually accepted them. And here's an example of a patch we sent to libosib. We have these two quite nasty loops, I think, and we just replace them with some relatively clean calls to stir-span. So to conclude, I presented a counterexample guided synthesis-based technique for summarization of simple loops in C. It was able to synthesize 88 of 115 loops, and it has applications in program analysis, compiler optimizations, and refactoring. Thank you.
Any questions?
Hi, this is really nice work. So you mentioned briefly that the evaluation was looking just at for the symbolic execution, just at the loops in isolation.
Yeah.
Did you also test this like on the whole program, and did you see like similar effects, less dramatic, or did you encounter any problems?
Well, the problem with running it on full programs is that we don't catch all the loops in the programs, and some of them are not really libc functions. Some of them are genuine loops. And when you gather constraints in theory of strings on character by character way, basically it doesn't work nearly as well, and it's way slower than the bit vectors and arrays. So you basically don't see this because you can't encode general loops as well in theory of strings.
Do you have an idea on how to fix this?
No. This was like a first step towards getting there, and yeah.
Do you have a sense of how many of the open-coded string loops are just sort of random stuff versus inline copies of libc functions that the programmer didn't know about versus hand-fused loops that are multiple libc functions together?
So you're saying how many loops are just like copied from libc and how many are like handcrafted and happen to have?
Yeah. Like I know when I'm doing this, I often write hand-fused string loops that do exactly what I want.
I was under the impression that they were mostly handwritten and happen to have the same behavior, and some people just don't know about stir-span. Some people don't like stir-char or memchar and just prefer like a two-line while loop.
Well, I guess the question is how many are composites of libc functions versus single libc functions? That was what I was trying to get at.
Yeah, we didn't really synthesize composites of libc functions just because we focused on single loops.
Well, I guess my point is that often a single loop will, if you unfuse it, you get two loops that are then libc functions.
I don't think any of any of the gadgets here aren't two loops. I mean, you mean like stir-span could be like two loops?
Yeah, like it might come out as a stir-span followed by memchar.
No.
Or vice versa.
We didn't see any of that, basically.
It's sort of interesting. Okay.